I'm going to start with one slide of introduction just to motivate the general context in which this work has been done. And this is the angular momentum of content of galaxies. And specifically, we have this fundamental plot here showing the specific angular momentum content of the stars in galaxies as a function of the stellar mass of the galaxy. And this galaxy is separated here to disk galaxies in blue and elliptical galaxies in red. And what we see is that we have two parallel sequences, which can also be described in some more detail with a continuum of morphological types of galaxies. And this plane reminds a lot of the similar relation for dark matter halos. So when one takes, with some empirical model, for example, takes the stellar mass and translates it to halo mass or connects each galaxy which halo mass it leaves, then one can draw these theoretical lines, the blue and the red lines, that correspond to a perfect conservation of angular momentum or retention of angular momentum and to some loss. And this perfect retention essentially postulates that each galaxy, the stellar component of each galaxy, has the same specific angular momentum as the mean dark matter halo of the mass that is postulated to host the galaxy. And this red line corresponds to about 80 or 90% loss of the specific angular momentum. So this is what I would like to explore, this rough equality between the specific angular momentum of stars and of the dark matter halos. So I'm going to start with some this very, very simple framework to think in a Lagrangian way about this problem. So I'm going to take this ratio that I just showed between the stellar specific angular momentum and the average angular momentum of a dark matter halo of the appropriate mass. And I'm just going to rewrite it in a very, very long form that will tell us how I'm thinking about it. So first I'm going to just open the specific angular momentum of the stars into the component, into essentially a weighted average of the two components, the in situ component and the ex situ component, and then divide by this average angular momentum of dark matter halos. Then what I'm going to do is just add in a series, divide by something, and then multiply by the same thing again, okay? And the result is going to be, after doing this a few times, I'm going to get ratios. In every line will be a ratio of two different things, and this ratio will represent something physical that I'd like to think about. Okay, so this is where we started, and I'm going to reveal a few things here. And what we get, this ratio I think is interesting, because what we have here is what we started with, the average specific angular momentum of halos. But in the numerator here we have the average specific angular momentum of disk harboring halos. And this is not necessarily the same thing, because if there is a correlation between the angular momentum of galaxies and their halos, then disks live in halos which have higher spin, and there is some scatter to the halo spin. So that means that this ratio will be larger than 1. And then if we'd like to explain a ratio of 1 here, then some of these other things will have to compensate this that is larger than 1. The next thing we can reveal is the ratio between the angular momentum of the dark matter that is associated with baryons that are going to make it into stars. So think about the initial conditions. We have dark matter and baryons. They're well mixed. But not every baryon is going to make it into stars. So I'm just going to think about the baryons that will, in the end, be stars, and think about the dark matter just near them in the same region. So this ratio compares the angular momentum of that dark matter associated with what will become stars and all of the dark matter that is accreted onto the halo. But the dark matter or the baryons that will become stars are not necessarily a fair representation of all the baryons in the initial region. So this may not be 1. Then we have the question of what is the actual angular momentum of the baryons versus the actual angular momentum of the dark matter when they accrete. And there are indications this may not be 1 either. And all this gray stuff is things that I'm not going to discuss. Everything that I did talk about are things happening outside of halos. All the gray stuff refers to things happening within halos and all the angular momentum changes that might occur. And this is not the topic of today's talk. So just to recap, there are a few quite different, conceptually different factors to think about. And we actually have indication that each of these things may be different from one. So let's just wrap up. this part, so we have the angular momentum at the time of accretion of the baryons with respect to dark matter. And an example that suggested this may be even a factor of 2 off is Danovich et al. 2014, where they showed that around the Virial radius, the gas actually has up to even twice as much specific angular momentum as dark matter. Then we have what I would call the angular momentum collapse bias, that the angular momentum at accretion of the baryons that will become stars versus of all the baryons. And this is some idea. This idea has been explored in a certain way in Susan Cassin's paper from 2012, where she imagined an inside-out collapse of the halo, and then pointed out that the angular momentum of the inner part of the halo is different from the angular momentum of all the halo, which will result, if only the inner part collapses into stars, which result in a different angular momentum for the stars and for the halo. Then we have the first point I mentioned, that the halos themselves that are harboring disks, which give us this ratio of 1, may not have the typical angular momentum. And this is even an assumption, a very old assumption, that the galaxy angular momentum is related to the halo angular momentum. And Vicente will talk about this more in the next talk. And finally, we have things that are happening. So essentially, the ratio between the final angular momentum of the stars at redshift 0 and the angular momentum that they had at the accretion time. And in a paper a couple of years ago with my student, we showed the progression of the angular momentum magnitude relative to the accretion as a function of some events that the gas is undergoing, for example, being accreted onto the galaxy, being blown out of the galaxy, actually converting from gas to stars, and we showed significant deviations from retention along this line, even for these galaxies. So that was the introduction, and now I'd like to jump into some results, and these are the various components or concepts that I will use. So I'm going to be focusing on 10 to the 12 solar mass halos in the illustrious TNG simulations. I'm going to contrast galaxies with high angular momentum and galaxies with low angular momentum. You can think about them very simplistically, as if you want, as disks and ellipticals, although it's not exactly like this. Then I'm going to consider the angular momentum vectors of both dark matter and stars. And for that, I will compare their magnitudes, as I've done so far, but also the relative angle between the two. And also, I'm going to look at redshift 0, as well as the same Lagrangian region. So I want to emphasize this because this is key to everything that I will show. I will select the galaxy or the stars at redshift 0 and the dark matter halo at redshift 0. And then either just follow the dark matter particles to the initial conditions or to very high redshift, or using tracer particles, follow the baryons that make up the stars. As I go backwards in time, at some point they will become gas. And so when I when I follow them to very, very early times, I will essentially be looking at gas. But this is the gas that at redshift 0 will be locked in stars. So this is what I mean by Lagrangian selection. And then I will also be relating a little bit to the dark matter only analog simulation of the full physics hydro simulations. Okay, so let's start again with magnitudes of angular momentum. Which we discussed so far. So here I'm comparing the specific angular momentum of the stars inside 10% of our VIR, so most of the stars in the halo for central galaxies, versus the total specific angular momentum of the dark matter. And we see a very poor correlation with a Pearson coefficient of 0.14. This is reminiscent of a paper that Fang Zhu posted earlier this year, where he looked at zoom-in simulations like Vela and Nihao, and also found this is not exactly the same quantity. He looked also at the cold gas and so on, but very similar picture overall. Very poor correlation between the baryon, between the galaxy, however you define it, and the total dark matter in terms of the magnitude. Now, inspired by a paper from Savala et al. From a few years ago, where he analyzed the Eagle simulation, instead of looking at the whole dark matter halo, I'm looking also at the inner dark matter halo. So now I'm looking both for stars and for dark matter within 10% of the virial radius. So each black point here is moving, has a purple point, where the purple shows with the same y-axis for the stars, but the x-axis now shows the angular momentum inside 10% of our VIR. And now we find a much better correlation. Significant scatter, but much better correlation in agreement with what is shown in the Eagle simulation. So let's explore this a bit as a function of radius, and now for the angle, not only for the magnitude. So what's shown here is the angle between the angular momenta of stars and dark matter enclosed as a function of radius. The thin line shows just individual galaxies, and this is the median in the black. So if we look at 10% of the Vero radius, sorry, you can't see the labels. This is 1% of the Vero radius, 10%, and the Vero radius itself. So if we look, we see there's, and I'm separating to the high J galaxies, so if you want disks, and low J if you want elliptical galaxies. So for these galaxies, we see a sweet spot around 5 or 10% of the Vero radius, where the angle between the enclosed in that radius, dark matter and stars, is just 4 degrees. And here in the bottom, we see the distribution of the cosine of this angle among the full population.
Can you just clarify, is this the simulations where you're measuring the dark matter in the hydro simulation?
That's in the hydro simulation still. The next slide will show the dark matter on the simulation. Yeah, so in the hydro simulation, for disk galaxies within kind of the disk radius, a few percent of our Vir, the dark matter has a very, very similarly oriented angular momentum to the stars. For galaxies that intrinsically have low angular momentum, this is much, much worse, but still far from a uniform distribution, which is what you will get for completely two random vectors in space. Okay, now, as Joe was suggesting, going to take yet another point for each of these galaxies, and now look at the angular momentum within 10% of the Vero radius in the dark matter only analogous simulation, and compared to the stars in the full hydro simulation. We still see, so the Pearson coefficient of the magnitudes becomes a bit worse from 0.5 to 0.3. Still, there's definitely some information there. And for the disk galaxies, it's actually only 15 degrees in the median. So the dark matter only simulation already knows where the disk is, how the disk is going to be oriented. For elliptical galaxies, it's much, much closer now to uniform distribution. Okay. So we'll focus now a bit more on the angles. And I want to just show a few images to give you a feeling for what are these high J and low J galaxies that I'm talking about. So this is a truly random selection showing edge on and face on, high J here and low J here. So you can see there are the low J ones are, some of them are disks. This is a very narrow mass range, around 10 to the 12 solar mass halos. So they're not all ellipticals, but some of them are bulge dominated, some are kind of elliptical, some are just small disks. Now I'm going to take on each sides of this slide, I'm going to take 4 examples and show an image of the stars and of in the inner part, in 10% RVR, and of the full dark matter halo, just from a random projection along the box. And now these are not face on or edge on. And the red line shows the direction of the angular momentum at redshift 0 of here for the stars and here for the dark matter. Now the lines are all normalized such that they all have the same length in 3D space. So if you see a short line, it means it's pointing inwards. Okay? So we see in most cases for the disk galaxies, they're pointing in the same similar direction, but here there is a case where they actually point in opposite direction. And you can see that this is a merging halo. So indeed, if you compare the inner galaxy and the full dark matter halo, this can be an origin of noise. For the low J galaxies, much more often they point in kind of in different ways, in different directions. And we can plot the, again, distributions of the cosine of these angles. So now this is not what we've seen before. Now it's the stars versus the full dark matter halo. So we see that for these galaxies, I mean, it's not bad. It's very far from uniform, but it's also definitely they're not pointing in the same way as the inner dark matter did. For low J galaxies, it's almost random at this point. And this reminds me actually of a plot from Frank van der Bosch from a few years ago, where he did a similar thing, but compared the angle between the dark matter and the gas, not the stars, and also found quite a broad distribution. And just a quick aside, again, Daniel De Filippis, who I mentioned earlier, a student working with me, is preparing a paper now where he compares the angle between the stars and the CGM the whole gas in the halo and also separating to cold and hot gas. And he finds that for high J galaxies, the alignment between the CGM and the stars is about 20 degrees in the median. For low J galaxies, about 60 degrees. And interestingly, hot and cold gas behave pretty similarly. So this is coming up in the next few months. And this picture is essentially the same as a function for all mass and redshifts. OK, this was a little aside. OK, so now coming back to these galaxies, now the yellow lines show the direction of the angular momentum of these same Lagrangian selections, but at redshift of 20. So completely in the nillinear regime, just to make it clear, it really does not matter if I'm taking redshift 10 or 20 or 50 here. Okay, so this is, and generally in the initial conditions, in the initial patch, they point in the same direction, except for those that I emphasized here. You can see that even in the initial direction, their initial time, they're pointing in different ways. How can this be? And again, these are the distributions of these these angles at the early time. So even for these galaxies, there's 25 degrees in the medium, even in the initial conditions. Compared to a redshift 0 distributions that we looked at, you can see that for disks, it's actually they're not so different in the initial time and at redshift 0. How can this be? So this is related to this accretion or collapse bias that I mentioned earlier. This is from a recent paper that shows at redshift 127, so the initial patch, gas and dark matter in red and black. And in this case, it's not the stars, it's all the gas that will end up in any dark matter halo. And you can see that the initial patches for dark matter and gas are not the same thing. So of course, in the initial conditions at this time, they will not necessarily have angular momenta that point in the same direction. And we can also compare within each panel the red and the yellow arrows that show essentially how the initial angular momentum and the final angular momentum compare in direction. And again, the histograms show us that for dark matter, this behaves differently between these two types of galaxies. The dark matter so again, I'm looking at the same particles at two different times. The dark matter reorients, or its angular momentum is being reoriented by about 30 degrees in the median over cosmic time. This is true also for the stars in these galaxies, but the stars in low J galaxies are almost completely reoriented in a random direction. So going back to, so the question that might come out from this is, so at least in these galaxies, do the dark matter and the stars reorient themselves over cosmic time in a similar way? And the answer, I think, is not. And we can see this by going back to the magnitudes. So we compare the magnitude of the angular momentum redshift 0 and at high redshift, and separately for dark matter in black and stars in green here. So we see there's an overall correlation. So you can see a halo that has high angular momentum. It already had high angular momentum at very, very early time, just from the Zeldovich approximation. But if we compare the evolution for the stars, so the difference between redshift 0 and high redshift, and the evolution for the dark matter, we see almost no correlation, even for the disk galaxies. So this means that the angular momentum evolution of the stars and the dark matter don't do the same. Is not the same. And a future direction to investigate is whether this is more to a result of something that happens before accretion or after accretion. Before accretion, it could be that they evolve in different ways simply because they come from somewhat different patches. Or it could be significant angular momentum loss, for example, of the baryons inside the halo that the dark matter does not experience. So I'll skip this and just summarize. So this is all work in progress. I'll be very happy to hear your thoughts, but a few takeaways that I think come out of the work I've done so far. So the empirically inferred relation that the angular momentum of magnitude of disks and of average dark matter halos are roughly equal may hide a lot under it. The angular momentum of stellar disks is more directly related to the inner dark matter halo than to the dark matter as a whole, and that's true both for magnitude and the direction. The inner dark matter halo in the gravity-only simulation, it already carries significant information, especially about the orientation, about what will happen to the baryons in the full physics simulation. We have this thing that I call angular momentum collapse bias, that the Lagrangian stars and dark matter are misaligned at high z, so that already accounts for some of the differences between the angular momentum of stars and dark matter today. What also adds to this is that each of these components is being reoriented over cosmic time, typically by 30 degrees, except for low angular momentum galaxies, which get kind of completely scrambled almost. They also don't, while the reorientation is roughly by 30 degrees for each of these components, in terms of magnitude, they evolve in almost independent ways. And this has to do with formation history, these last two slides that I skipped, so we won't talk about that, but Vicente will talk a lot about merger history, so I'll stop here.
We have time for questions. Students first. Any students, postdocs? Joe?
Sorry, very good, very interesting. You mentioned that this doesn't look like tidal torque theory. It doesn't look like tidal torque theory at all. The standard tidal torque theory picture, Fred Boyle, Tim Peeble, Simon White et al., is that the angular momentum is essentially zero until the collapse occurs and we get so that maximum expansion, quadrupole interactions, and those then generate the rotation, and of course this stops as they separate because of cosmic expansion. Now, if in fact at redshift 20, before, as you said, it's a linear regime, collapses haven't occurred yet. If there's already a lot of angular momentum information there.
No, so I think I think this is actually consistent with tidal torque theory. It's just before turnaround, the angular momentum just grows with a growth factor. But if you assume that the configuration of the cosmic web is constant, it just grows over time. It's just being torqued more and more over time. And you can calculate at what rate it grows in the linear regime. And this is actually this overall magnitude difference between now and high redshift is actually consistent with the growth in the linear regime if we assume a turnaround time of roughly redshift 2 or something like this. So in that sense, this overall magnitude is consistent with tidal torque theory.
Brian?
Yeah, I was very puzzled by this dramatic difference in the Lagrangian volumes for the gas and the dark matter. And you call it an accretion bias, but or collapse bias, but so what is black is dark matter?
Black is dark matter and
dark matter regions that come in that don't have any corresponding gas.
yeah, so here all gas that was in this region in the initial condition did not end up in the same halo as all the rest of it.
Feedback.
So this is not my work. This is not my work, and this is work based on adiabatic simulation. So no cooling. Yeah. So with feedback, I haven't looked specifically, but I think it may be even more complicated. They give a few explanations. It's a very short paper. They give kind of a page of a few ideas. For example, kind of dark matter. For example, one idea is pancake stripping. So if a galaxy goes through a pancake, the gas feels the Ram pressure, the dark matter doesn't, and then they separate forever. Things like this.
Okay, so maybe one more question while the next speaker sets up.
When you were comparing the magnitude of the angular momentum of the stars and the dark matter in the central halo, the angular momentum of the stars seem to always be systematically higher than the angular momentum of the dark matter in the central halo. Is there an easy explanation for that? It was toward the beginning of your. Yeah, all the pink points are
I
about
see.
the one-to-one line.
Yeah, that's a good point. So I can't say for sure, but I would say that the dark matter, I would be interested in seeing what this looks like without feedback. So I think we have shown that feedback actually can account for an increase in the overall angular momentum of the stars. So I think maybe without feedback you would get them behaving more similarly. Nothing can kind of counteract the losses that the inner dark matter halo has experienced. But
Okay, so let's thank the Shai again.
thank you.